Byte pair encoding is one of the simplest ideas behind modern language models. You start with tiny pieces of text and repeatedly glue together the pairs that appear most often. By the end of this video, you'll see exactly how byte pair encoding builds tokens step by step, why that helps a language model, and how vocabulary size trades off against sequence length. We are not just going to talk about it, we are going to watch it happen live using an interactive demo. Welcome to Schovia Labs, where we turn AI ideas into everyday intuition. Let's start with the problem that byte pair encoding solves. Language models do not read raw text the way we do. They first break text into units called tokens. These tokens might be words, they may be pieces of words, or even characters. Now, if we tokenize only by full words, we get a big problem. The vocabulary size explodes because of rare words, new words, names, misspellings, technical terms, etc. If we tokenize only by characters, we avoid unknown words. But sequences become very long, which means this paragraph of text that you see here is represented by 172 tokens. When we use this in a large language model that has a limited context size, it can only process a small amount of information at once. Context size is how much text a model can process at once. But if we are smarter and add a few other items in our vocabulary, like more and summers, the same paragraph can be represented in 152 tokens. This is an important saving for a large language model. Not whole words all the time, not just single characters either, but reusable subword pieces. And that's exactly what byte pair encoding does. It starts with characters and then repeatedly merges the most frequent adjacent pairs into a new token. This compression style idea was adapted into Subword tokenization and became widely used in the modern natural language processing systems. Today, we'll use this byte pair encoding demo to see that process unfold in an interactive way. Before touching the tool, here's the core idea. Imagine our text contains words like low, lower, lowest, newer, and newest. If we begin with characters, the model sees something like this. Now, byte pair encoding asks, what adjacent pairs appear the most often? Maybe it sees that L and O appear together a lot. So it creates a new item in the vocabulary, which is LO. Then it might see that LO and W occur quite frequently together. It can then create a new item in the vocabulary called low. Similarly, it might see that E and R appear together a lot, or E and S appear together a lot. It merges the most frequent pairs first, and then it keeps repeating this process. What this means is that byte pair encoding doesn't learn tokens because they are words in the human sense. It learns them because they are frequent building blocks. In summary, byte pair encoding is a frequency-driven merging. Every round of byte pair encoding adds one new token to the vocabulary by merging the most frequent adjacent pairs. So vocabulary size goes up, but context size, which is the number of tokens needed to represent this text, usually goes down. At the beginning, the tokenizer knows only the smallest building blocks. That makes it universal, but it's inefficient. It can spell anything, but it also has to spell it really slowly. So this is the first learned subword. Byte pair encoding looked across the training text, it counted the adjacent pairs and picked the one that appeared most often. And that pair becomes a new token. Now let's run a few more rounds. Now you can start to see the tokenizer building reusable chunks. At first, the merges often looked small and local, like maybe pairs of characters that frequently sit next to each other. But after enough rounds, those merged chunks themselves can be merged again, creating longer and more meaningful subword units. This table is basically byte pair encoding's decision queue. It tells us which adjacent token pairs are currently winning the frequency contest. The pair at the top is the one byte pair encoding is most likely to merge next. This chart here shows the trade-off in byte pair encoding. Every time we add a merged token, the vocabulary gets bigger, but the text can now be represented with fewer pieces. So the context size drops. So I hope seeing the demo helped. A link for you to interact with this demo has been posted in the description of the video. So let's wrap up with some intuition of why byte pair encoding helps. So suppose a large language model sees a rare word like unhappiness. If it only knew whole words, that word might be rare or missing. If it only used characters, it could represent it, but in too many tiny steps. Byte pair encoding can often break it into useful chunks like UN, happy, and ness. Maybe not exactly those in every tokenizer, but that's the spirit. It learns recurring pieces that appear across many words. So instead of memorizing every word independently, the model reuses subword building blocks. This is why byte pair encoding helps with rare words, new words, misspellings, names, and domain specific terms. This subword idea was a major reason byte pair encoding style segmentation became influential in natural language processing. As we run more rounds, the tokenizer keeps absorbing frequent patterns into bigger tokens. The vocabulary grows, and the sequence needed to represent the original text keeps shrinking. But there's a trade off. If you keep merging forever, you may end up memorizing too many specific chunks. This can make the vocabulary large and less reusable. So, the big takeaway is that byte pair encoding builds a subword vocabulary by frequency and not by handwritten rules. That gives the language model a sweet spot between giant word vocabularies and overly long character sequences. That's why sometimes byte pair encoding tokens look intuitive and sometimes they just look a little weird. They're optimized for reuse and compression, not for meaning or elegance. Before an LLM predicts the next token, it needs the text converted into tokens first. And byte pair encoding style tokenization is one of the major ways this happens in practice. Note that this vocabulary building exercise is done by large language models on very large amounts of data, unlike the simple example we showed in the demo. So that's a wrap. Thanks for joining us on Schovia Labs. Hit that subscribe button for more eye opening insights. And as always, stay curious.